In 12 days, something that has never happened in recorded human history is going to happen. An object from another star system is going to pass through Jupiter's gravitational sphere of influence, not near it, not past it at a safe distance, through it, deep inside the boundary where Jupiter's gravity overpowers the Sun's, a boundary called the Hill sphere, a boundary that, once crossed, makes you, temporarily, a satellite of the largest planet in our solar system. 3I Atlas, the interstellar comet that has been producing anomalous data since the moment it was discovered in July 2025. The object with a CO2 to water ratio sitting 4.5 sigma outside the solar system trend. The object whose three jets are separated by exactly 120 degrees. The object that Avi Loeb has listed 15 separate anomalies for in published papers. That object reaches Jupiter on March 16, 2026. And what happens during those hours inside Jupiter's Hill sphere is not just a gravitational footnote on the way out of our solar system. It is the last major scientific event we will ever have with 3I Atlas, the last time any instrument we have will be close enough to measure something meaningful, the last chapter. But here is what nobody is talking about. Avi Loeb published a paper in November 2025 calculating something extraordinary. The closest approach distance of 3I Atlas to Jupiter is, within one standard deviation, exactly equal to Jupiter's Hill radius, not approximately, not roughly, exactly, to a precision of 1 part in 26,000. That number is either the most extraordinary coincidence in the history of interstellar object observations, or it is not a coincidence at all. Today we go through everything: the physics of the Jupiter encounter, what the tidal forces will do to 3I Atlas, what instruments are watching, what Loeb's calculation means, and what the next 12 days could reveal that changes how we understand everything that came before. Stay with me. What the Hill sphere is, and why March 16th is different. To understand why March 16th matters, you need to understand the Hill sphere, because this concept is at the center of everything that makes the upcoming encounter extraordinary. Every planet in the solar system has a gravitational sphere of influence, a region of space around it where its own gravity dominates over the Sun's tidal forces. Within this region, objects can maintain stable orbits around the planet rather than being pulled away by the Sun. This region is called the Hill sphere, named after the 19th century astronomer George William Hill. For Jupiter, the Hill sphere is enormous. Jupiter is the most massive planet in the solar system, 318 times the mass of Earth, and its gravitational reach is correspondingly vast. Jupiter's Hill radius on March 16, 2026, calculated precisely by Avi Loeb using NASA's JPL Horizons orbital data, is 53,502 million kilometers. On March 16th, 3I Atlas will pass Jupiter at a closest approach distance that JPL Horizons calculates as essentially identical to that Hill radius, within 0.06 million kilometers of the exact boundary, at a distance of roughly 53.56 million kilometers from Jupiter. What this means physically is that 3I Atlas will graze the edge of Jupiter's gravitational dominance zone. For a brief window around closest approach, it will be on the boundary between being a Sun-orbiting object and being a Jupiter-orbiting object. The gravitational forces from the Sun and from Jupiter will be nearly in balance. This has two immediate consequences. First, Jupiter will exert a gravitational slingshot effect on 3I Atlas. The object's trajectory will be altered. Its outbound velocity will change. The exact magnitude of that change depends on the precise geometry of the encounter, but the directional change will be measurable. 3I Atlas will exit our solar system on a slightly different path than it would have without this encounter. Second, The tidal forces from Jupiter at this distance will stress 3I Atlas's nucleus. Tidal forces are differential gravity. The side of 3I Atlas facing Jupiter will be pulled slightly harder than the side facing away. For a solid rock, these forces are negligible. For a loosely consolidated icy body, they can cause fracturing, outgassing, and, in extreme cases, fragmentation. The most dramatic historical example is comet Shoemaker-Levy 9, which was torn apart by Jupiter's tidal forces in 1992 and crashed into the planet in 21 separate fragments in 1994. 3I Atlas is not going to hit Jupiter. It is not going to be torn apart the way Shoemaker-Levy 9 was. The geometry is different, and the tidal stress will be less extreme, but the encounter will stress the nucleus in measurable ways, and how 3I Atlas responds to that stress will tell us things about its internal structure that no other observation can. The coincidence that isn't Loeb's calculation. Now I want to spend serious time on Avi Loeb's November 2025 paper, because the calculation he published is the most scientifically provocative finding connected to the Jupiter encounter, and it has not received the attention it deserves. Loeb calculated Jupiter's Hill radius for March 16, 2026. The result was 53,502 million kilometers. He then looked at the JPL Horizon's prediction for 3I Atlas's closest approach, distance to Jupiter, on the same date. The result was 53.56 million kilometers. The difference between these two numbers is 0.06 million kilometers. That is 60,000 kilometers, smaller than Jupiter's own radius. In other words, 3I Atlas's closest approach to Jupiter is, within measurement uncertainty, exactly at Jupiter's Hill sphere boundary. Loeb then asked how statistically rare this coincidence is. He reasoned as follows: 3I Atlas's non-gravitational acceleration, the small extra push it receives from its own outgassing as it moves through space, was measured during its perihelion passage in late October 2025. The measured non-gravitational acceleration value shifted the predicted minimum distance from Jupiter by approximately 0.1 million kilometers. Without that specific non-gravitational acceleration value, the closest approach distance would have been different. Loeb calculates that the probability of the closest approach distance landing within 0.06 million kilometers of the Hill radius, given the full range of possible trajectories across Jupiter's orbital diameter, is approximately 1 in 26,000. 1 in 26,000. That is a 0.004% probability. Loeb's interpretation is careful but pointed. He does not claim this is proof of anything. He frames it as an extraordinary anomaly that warrants attention, but he raises a specific possibility. If 3I Atlas is a technological object, the jets observed around its nucleus in post-perihelion images could have been used for a minor orbital correction during perihelion, when the object was hidden behind the Sun from Earth-based observatories. A small maneuver at perihelion, using the Sun's gravitational assist, could have adjusted the trajectory precisely enough to produce a closest approach distance to Jupiter equal to the Hill radius. Why would that be a target? The Hill sphere boundary is scientifically optimal for depositing objects into stable orbit around Jupiter with minimal energy expenditure. The Lagrange points L1 and L2 are located at the Hill radius. Objects placed near those points require minimal orbital correction to maintain stable orbits indefinitely. Loeb's hypothesis, stated hypothetically and carefully, is that if 3I Atlas were a technological object designed to deposit something into Jupiter's gravitational sphere, the optimal delivery mechanism would be exactly the trajectory it is currently following. A closest approach distance equal to the Hill radius approached at hyperbolic velocity, passing through the L1 and L2 equilibrium points. I want to be very clear. This is a hypothesis. It is not established science. The mainstream scientific consensus is that 3I Atlas is a natural interstellar comet whose trajectory is the result of its natural history and the measured non-gravitational acceleration from outgassing. But 1 in 26,000 is a number that deserves to be stated clearly and examined honestly, and the examination is what the next 12 days will enable. What tidal stress will do to 3I Atlas. Setting aside the Loeb hypothesis for a moment, let's talk about the physics of what Jupiter's gravity will actually do to 3I Atlas during the encounter. Because regardless of what the object is, the encounter will be scientifically revealing. Tidal forces work by pulling the near side of an object harder than the far side. The difference in gravitational force across an object creates a stretching effect. For a small, rigid object, this stress is too small to matter. For a large, loosely consolidated cometary nucleus, it can be significant. 3I Atlas's nucleus is estimated at approximately 2.6 kilometers in diameter based on post-perihelion Hubble observations. At its closest approach distance of 53.56 million kilometers from Jupiter, the tidal acceleration across a nucleus of that size is calculable. The differential force will not be large enough to cause catastrophic disruption at this distance, but it may be large enough to cause enhanced outgassing. Enhanced outgassing, triggered by tidal stress, works through a specific mechanism. Tidal forces create microfractures in the nucleus surface. These fractures open pathways for subsurface volatiles, gases that are trapped beneath the surface under pressure, to escape. The result is outbursts, sudden increases in coma brightness and gas production that are detectable from Earth. The Minor Planet Center is currently refining 3I Atlas's trajectory to determine the precise geometry of the encounter. Their models, which incorporate hundreds of Monte Carlo simulations with orbital uncertainties, predict a measurable perturbation to the trajectory and the possibility of tidal stress-induced outbursts in the days around March 16th. Crucially, the composition of any outburst material will be diagnostic. During the approach to the Sun, 3I Atlas's surface volatiles were depleted. Webb's December 2025 MIRI observation showed that post-perihelion outgassing has shifted from CO2-dominated to CO-dominated, consistent with the surface CO2 being largely exhausted and the deeper CO reservoir now driving activity. If tidal stress during the Jupiter encounter opens fractures that reach even deeper into the nucleus, the outburst material could include volatiles from the most pristine interior layers, methane, more CO, possibly molecular species that have not yet been detected in 3I Atlas's coma, material that has been locked inside since the object formed billions of years ago in another planetary system. The Jupiter encounter is not just a gravitational interaction, it is potentially a geological event, a stress test that may crack open the interior of an interstellar object and let us read what's inside. What instruments are watching and what they can see. The scientific community has been preparing for March 16th for months. Let me go through what instruments are positioned to observe the encounter and what each one can contribute. The most exciting possibility is NASA's Juno spacecraft. Juno has been in orbit around Jupiter since 2016. Its primary mission to study Jupiter's interior and magnetic field is largely complete, but the spacecraft remains operational and its JunoCam instrument continues to function. The Minor Planet Center is actively refining trajectory calculations to determine whether Juno can be pointed toward 3I Atlas during the encounter window. If Juno can image 3I Atlas during the flyby, the result would be the closest range observation ever obtained of an interstellar object. Even a low-resolution JunoCam detection would constrain nucleus size estimates and potentially reveal coma structure at a resolution no Earth-based or Earth-orbiting telescope can achieve at this distance. The Juno observation window is calculated as March 9th through 22nd. Mission controllers are evaluating whether the orbital geometry allows pointing the spacecraft toward 3I Atlas without compromising Juno's primary operational requirements. The decision is pending. Ground-based observatories will be watching continuously. The Very Large Telescope, Gemini Observatory, and other major facilities have observation campaigns planned around the encounter. Spectroscopic monitoring before, during, and after closest approach will track any changes in the comet's molecular composition. If tidal stress triggers outbursts, the timing, brightness, and spectral content of those outbursts will be recorded. The Hubble Space Telescope, which has been observing 3I Atlas intermittently since its discovery, may conduct targeted observations around the encounter to track any morphological changes in the coma and nucleus region. And there is the JUICE spacecraft. JUICE observed 3I Atlas in November 2025 with 5 instruments, and the full dataset has only recently been received and is currently being analyzed. The JUICE instrument teams are meeting in late March to discuss their findings, a timing that is not coincidental. The Jupiter encounter happens March 16th. The team meeting happens in the days following. Whatever the encounter produces, the JUICE team will be reviewing it in the context of the most comprehensive close-range dataset ever collected on this object. The trajectory change, what it reveals. One of the most scientifically valuable measurements that will come out of the March 16th encounter is the precise trajectory change that Jupiter's gravity imparts to 3I Atlas. This matters for several reasons. First, the exact trajectory change constrains the object's mass. Gravitational deflection depends on the geometry of the encounter and the masses of the objects involved. Jupiter's mass is known with extraordinary precision. 3I Atlas's closest approach distance will be measured with high accuracy by astrometric observations from multiple observatories. The combination of these measurements allows the deflection angle to be calculated with precision, and the deflection angle compared against what Newtonian gravity predicts for a massless test particle can reveal whether 3I Atlas's own mass plays any measurable role in the interaction. For an object of 2.6 kilometers diameter with typical cometary density, the mass is small enough that self-gravity effects on the trajectory are negligible. But if 3I Atlas has an anomalously high density, something that would be indicated by a smaller than expected tidal deflection, that would be a detectable signal. Second, the post-encounter trajectory defines 3I Atlas's exit path from the solar system. After March 16th, the object will be on its final outbound trajectory. Measuring that trajectory precisely and comparing it against predictions that include and exclude non-gravitational forces from continuing outgassing will allow scientists to map the object's outgassing activity in the outer solar system as it fades. Third, and most relevant to the Loeb hypothesis, the post-encounter trajectory will confirm whether any trajectory correction occurred around perihelion. If the measured post-encounter path is consistent with a purely natural trajectory governed only by gravity and measured non-gravitational forces, the coincidence between the closest approach distance and the hill radius was natural. If the post-encounter trajectory shows any residual unexplained deflection, that would require a new explanation. The astrometric data from the encounter will be among the most precisely measured orbital data ever collected for an interstellar object. And precise orbital data is how you distinguish natural from non-natural dynamics. The activity shift from CO2 to CO and what comes next. I want to spend time on where 3I Atlas's outgassing activity stands right now as it approaches the encounter, because the current state of its activity shapes what the Jupiter flyby will reveal. Webb's December 2025 MIRI observation established that post-perihelion outgassing had shifted from CO2-dominated to CO-dominated. The surface CO2 reservoir, which drove the anomalously high activity before and during perihelion, has been substantially depleted by solar heating during the closest approach to the Sun. The 3I Atlas tracking site, which aggregates observational data from the global amateur and professional community, notes that, as of early February 2026, the coma has contracted from its peak diameter to approximately 1.8 arc-minutes, and the dust tail has shortened to roughly 6 arc-minutes. The object is fading as it moves outward and cools. But CO outgassing continues. Carbon monoxide sublimates at much lower temperatures than CO2 or water, remaining active at large distances from the Sun. As 3I Atlas moves toward Jupiter's distance and beyond, CO will be the primary driver of whatever residual activity remains. The Jupiter tidal stress encounter changes this picture in a specific way. Tidal stress-induced fracturing, if it occurs, will not primarily release CO from the surface. It will expose subsurface material, fresh material that has not been depleted by solar heating, material that may still contain CO2 and even methane from the deep interior. A tidal stress outburst from 3I Atlas could therefore look chemically different from its normal post-perihelion activity. A sudden increase in CO2, or the detection of new molecular species from the deep interior appearing in the hours and days around March 16th, would be a direct measurement of what is buried beneath 3I Atlas's surface, a chemical core sample from another planetary system, obtained not by drilling, but by gravitational stress. This is what the spectrographic teams are watching for, not just whether an outburst occurs, but what it is made of. What happens after Jupiter, the final exit? After March 16th, 3I Atlas is done with our solar system. Let me put the post-encounter timeline on the table because it frames the urgency of what the next 12 days represent. After the Jupiter encounter, 3I Atlas will be on its final exit trajectory. Its velocity, which has been decreasing since perihelion as the Sun's gravity works against it, will receive a slight boost from the Jupiter slingshot, depending on the geometry. It will then continue outward. In July 2026, it will cross Saturn's orbit. By April 2027, it will pass Uranus's orbit. By 2028, Neptune's orbit. After that, it enters the Oort cloud region and eventually interstellar space, never to return. The observational window from Earth-based telescopes is already effectively closing. At its current magnitude of approximately 16.7, 3I Atlas requires an 8-inch telescope or larger to detect. After the Jupiter encounter, it will fade further as it moves away from the Sun. By mid-2026, only the largest professional telescopes will be able to track it. This means that March 16th is not just an astronomical event, it is a deadline, the last moment when Jupiter's proximity gives any instrument positioned in that region of the solar system a chance to collect data at meaningful resolution, the last major perturbation that will generate measurable signatures, the last chapter before the book closes. And it is happening in 12 days. The scientific community knows this. The observation campaigns are planned. The instruments are being pointed. The models are being refined. Whatever 3I Atlas is, whatever it reveals during those hours inside Jupiter's Hill sphere, will be the final entry in the data record of the only interstellar object we have ever been able to study at this level of detail. Bigger picture, what 3I Atlas has already changed. Before we close, I want to step back and look at what 3I Atlas has already changed. Regardless of what happens on March 16th, regardless of whether the Jupiter encounter produces outbursts or quiet passage, regardless of whether Juno gets a picture. 3I Atlas has changed three things permanently. First, it has proven that interstellar comets carry chemically specific information about their home planetary systems. Webb's detection of a CO2 to water ratio 4.5 sigma above the solar system trend is not just a measurement of one object, it is proof of concept that the universe makes planetary systems with different chemistry than ours, that the specific molecular inventory of a cometary nucleus is a readable fingerprint of a star system we cannot visit. Every interstellar object that passes through our solar system from now on is a chemical sample from somewhere else. We now know how to read those samples. Second, it has established Avi Loeb's framework of interstellar archaeology as a legitimate scientific program. Whether or not any specific anomaly of 3I Atlas turns out to have a non-natural explanation, the systematic documentation of 15 anomalies, the publication of papers calculating coincidence probabilities, the framing of the Jupiter encounter as a test of specific hypotheses, this is rigorous scientific methodology applied to a genuinely extraordinary object. The program has produced real results and will produce more. Third, it has demonstrated the value of the global observational infrastructure that humanity has built. Hubble, Webb, JUICE, TESS, SWIFT, Parker Solar Probe, SphereX, Juno, Europa Clipper, the Mars orbiters, the Very Large Telescope, Gemini, dozens of ground-based facilities, all of them contributed to the most comprehensive characterization ever achieved of an object from outside our solar system. That infrastructure exists. It worked, and the next interstellar object that enters our solar system will be studied even better. 3I Atlas arrived in July 2025. It will effectively leave in March 2026. 9 months. In 9 months, humanity went from knowing nothing about this object to having CO2 isotopic ratios, methane outgassing patterns, jet geometry measurements, nucleus size estimates, tidal activity predictions, and gravitational deflection calculations ready for the final encounter. That is not nothing, that is extraordinary. March 16, 2026, 53.56 million kilometers from Jupiter, 1 standard deviation from the exact boundary of Jupiter's gravitational sphere of influence, 1 in 26,000 probability of coincidence, a tidal stress encounter that may crack open the most pristine interior of an interstellar nucleus, potential outbursts carrying chemistry from the deep interior of another planetary system, a possible Juno observation, a JUICE science team meeting scheduled for late March to review everything, and after that silence, fading, Saturn's orbit in July, Uranus in 2027, Neptune in 2028, then gone, forever. 12 days. That is what remains of the most scientifically significant object to visit our solar system in human history. Whatever 3I Atlas is, a natural cometary relic from a cold CO2-rich protoplanetary disk orbiting an old star in a metal-poor region of the galaxy, or something that Loeb's 1 in 26,000 calculation hints at. The Jupiter encounter is the last moment we have to find out. The instruments are pointing, the models are running, the trajectory is locked. In 12 days, we get our final answer. Subscribe so you don't miss the coverage when the data comes in. Share this with someone who doesn't realize what's about to happen. And drop a comment telling me what you think the Jupiter encounter will reveal. Because March 16th is not the end of the story, it is the last page, and last pages matter.